All right, welcome back. In this week's lesson, we're going to talk about the normal distribution and area under the curve. But in order to remind us where we are, we have to go back to what we've covered. So as you may remember in the previous lecture, we talked about z-scores and z-scores being quite meaningful when you're using a normal distribution. Now, the normal distribution is a theoretical abstraction. It's also referred to as the bell curve. And the normal distribution or bell curve has certain properties. The first is that it is unimodal. As you remember from earlier lessons, the word uni means one, modal means peak. So a normal distribution has one peak. It's really high at the middle, and then it gets smaller as we move to the tails. It's symmetrical. That is to say, the positive side of the normal distribution and the negative side of the normal distribution are the same. Now, for something to be symmetrical, you should be able to fold it on top of itself, and it should be a perfect overlay. So in a normal distribution, the negative side of the curve and the positive side of the curve overlay perfectly. And it's asymptotic. Basically, that's a fancy way of saying the tails go until infinity. They go all the way to the end. So when we ask ourselves, well, I know the normal distribution in principle, but what kind of examples could I provide of a normal distribution? Well, all naturally occurring phenomenon approximate a normal distribution. So things like height is on a bell curve, right? There's an average height for males, there's an average height for females. And then as you move away from the average, fewer and fewer people tend to have it. So really tall people and really short people are actually rarer than people who are closer to the midline. Now, we also need to understand the concept of area under the curve. Area under the curve is the percent of the population that falls between 2 points. And when we talk about a normal distribution, we usually do a reference point from the mean. Now, let me just go up to the board and show you some certain principles. All right, so here we are. And I'm gonna actually stop the share so it's in full view. But here we are. I don't know if you can see, but here's a bell-shaped curve, right? So it has 50% on one side, and it has 50% on the other side. So if we were to take the whole bell curve, we were to add that up, we would get 100%, right? Between this side and between that side. So that's that. Now, I said in the last lecture, the mean is marked as 0, and we have points along the way where we have the negative side, which is -1, -2, -3. And it could go on. Remember, it's asymptotic. It goes on till infinity. And then we have the positive side. So we have +1, +2, +3. And I just want to do a check to make sure it actually is showing up on the video. I'm not sure. So I'm going to move it closer so you could see better. All right. So, yeah. So again, you have 50% on the negative side, 50% on the positive side. The whole bell curve is 100%. And we have a -1, -2, -3, +1, +2, +3. And you might ask me, well, why am I only stopping at 3? Well, the answer is that about 99.7% of the cases can be found plus or minus 3 standard deviations from the mean. Now let's go back into the slides. So we said area under the curve allows us to compare between 2 points. Now, the whole bell curve would be 100%, as I said. And typically, when we compare 2 points, the most common place is the mean. So we do a reference point of the mean. Okay. So when you think of score distributions, we use, as I said, area under the curve to determine percentage of cases found. Now, this can be found in the back of your book. Now, I have an older edition of the book that I use. I don't know if you can see, but this is Walkowitz, Ewing, and Cohen. And in the back of the book, you have a table called, I don't know if you could see the title, but it says percent area under the normal curve between the mean score and the z-score, right? So you'll always be able to calculate area under the curve. Not every book is going to do area under the curve between the mean and the z-score. Some actually just go from the beginning of the bell curve, starting at the negative tail all the way to the positive tail. But I find that this is actually more useful. That's actually why I use it. All right. So as you may remember, the average on when we plot on a bell curve is 0. Remember that from last class. And the standard deviation are units of 1, whether they be positive or negative. And as I said, we have the table that we can calculate exact area under the curve. Now, depending on your book, this could be table A, or this could be table B. In the older edition, it's table B. But either way, you're looking, the title didn't change in the editions, percent area under the curve between Z and the mean. Now, I do want to take you through this if you're ever reading an area under the curve table, right? So if we go vertical, right? So when we talk about going down, it's in units of 1/10 of a point going down. And if we go across, it's units of 100ths of a point. So going down, we have the whole number and the tens place. Going across, we have the 100ths place, or the second decimal point. So if we were to go to the table and we'll say, okay, well, what would a z-score of +1 be? So I go into my book and I go down to 1.0, and then it's 1.000. So it would indicate 34.13%. So the percent of cases that occur between the mean and between +1.0 is 34%. Now I'm gonna do another bell curve in a minute. Now, if we were doing a negative z-score of 1.0, it would be the same. The table does not show negative numbers because it's symmetrical, right? So the number would be the same. So if it's negative 1.00, it would also be 34.13%. So interesting to note, and I'm going to do the graph now, is I'm going to erase this. If we were to draw a line on both sides of the bell curve, right? And bracket it. I'm going to see if I have another marker because this one's dying on me. But if we were to bracket on both positive and negative side, we would get 68%. So let me see if this one works better. Yes. So for one standard deviation plus or minus, we have 34.13% here, 34.13% here. Together, if we want to know what's the percent of cases between one standard deviation plus or minus, we're going to get 68.26%. All right. Now, what if we wanted to know the percent of cases that occur between two standard deviations plus or minus on the bell curve? Well, we have to go back to our book. I go down to 2.0, go across, we get 47.72. I don't know if you can see that, but 47.72. So 47.72% here, 47.72% here. Now, remember, what this is doing is we're trying to figure out area under the curve between positive and negative two standard deviations. Okay, so what I would do is I would add 47.73 because that 47.73 is between -2 and 0 plus another 47.72, and I would get something that looks like 95.44%. So 95% of the cases will occur between positive and -2 standard deviations. What about 3? Well, let's go up here. Okay, and I guess I should redraw my bell curve so you can see it. Right? All right, so what about here? So I would go down to my book again, find 3.0, and then I have 49.87. 49.87%. 49.87%. So now again, if I'm looking for 3 standard deviations, I'm comparing all the way across. So I have to add this side with this side. So what's 49.87 plus 49.87? Well, I can't do that one mental math. So let me get back to using my calculator, right? When in doubt, use your calculator. And here we are. So we do 49.87 plus 49.87 hit equal, and we get 99.74. So 99.74%. So what am I trying to teach you here? I'm trying to explain to you that 68% of the cases occur plus or minus 1 standard deviation. 95% of the cases occur between 2 standard deviations. 99% of the cases occur between 3 standard deviations. only about 0.3% of the cases are further along in the distribution than plus or minus 3. So that's why in most cases, when people draw the bell curve, they sometimes draw the bell curve and stop at plus or minus 3. It's not that there isn't anything else there. It's that most of the cases fall within that parameter. Another important point when we're talking about area under the curve, it's remarkable because the closer you are to the mean, the more cases are, right? So actually, the distance between 0 to 1 is there are more cases than 1 to 2. Because as I said, the bell curve, as you go further to the tail, fewer and fewer cases occur. All right, so we could use this table to calculate percentile rank, which is at a certain mark. Remember, the definition of percentile rank was the percent of cases that occur at or below a point. And we can also use this table to calculate area between two different z-scores. So I already did this on the board, right? But you saw the area under the curve for plus or minus 1 z-score or 1 standard deviation is 68.26, 95.442. Now, I also said this. It's interesting that the distance between 0 to 1 was 34.13%. The distance between 1 to 2 is only 13.59%, right? So as you go further, the percent of cases get smaller and smaller. Now here is just another graph. Instead of using whole percents, it's using it as a decimal point, right? So same thing we've already said. Now, let's say, and I'm going to do some demos now, and I'm going to clear this bell curve up. I said you could figure out percentile rank. I said you could figure out the area between two z-scores. So let's see what we can do. All right. I'm going to take these two questions and I'm going to put them on the board, or 3 questions, forgive me. And I'm going to show you how to calculate them. So let me stop my share and let me pause the recording to set up. All right, so here we are. I just drew a blank bell curve. And the first question asks what percent of the cases would occur on an SAT between 480 and 520? Well, we have to calculate 2 z-scores. That's the first thing we're going to do. So let's do z is 480 minus 500, which was the mean, divided by 100. Now you may remember the z-score formula. Z was equal to x minus mu divided by standard deviation, right? So this first one we're going to do 480 minus 550 is minus 20 divided by 100 gives us negative 0.20. Now with the z-score, we're going 2 decimal places, right? Because the table goes 2 decimal places. So we now know that the first place we're going to mark is minus 0.2. Now the second one is 520. So we're going to do the same formula. Z equals 520 minus 500 divided by 100, which gives me 20 over 100, which gives me positive 0.20. Now remember, this side of the curve is your negative side. This is positive 0.2. So we're going to mark this here as positive 0.2. And now I'm going to draw my lines to create space between the two. So I'm going to go to my table. And in the book, it says positive 2.0 area under the curve is 7.93. Now I'm going to show you that right there, 7.93. And so negative and positive are the same, 7.93 and 7.93. Now the question is, what percent of cases occur between 480 and 520? So I want to know what percent of cases occur between the two. The general rule is that if you cross the midline, you add. So to calculate this one, we do 7.93 plus 7.93, which gives us 15.86%. So that's how you do the first one. Step one, draw the bell curve. Step two, calculate your z-scores. Step three, go to the back of the book. Step four, plot it on the bell curve. Step five, add or subtract accordingly. So this first one is an example where we would add. So let me erase this, start over, right? And we're going to do another one. The second question on the slides was, what's the percent of the cases between 350 and 450? Okay, no problem. So we still have to calculate our z-score. So step one, I drew my bell curve. Step two, calculate my z-scores. Now, just as a reminder, z-score is your individual score minus the mean. This time I'm going to draw the mean as a sample mean because I think that's how I wrote it. X minus X bar divided by standard deviation. So first one is 350. So we do 350 minus 500 over 100, which gives us negative 150 over 100, or negative 1.50. That's our first one. The second data point is 450. 450 minus 500 divided by 100 equals 50 in the negative over 100, or equal to minus 0.50. Okay, so step three, I calculated my z-scores. Now I'm going to plot it, right? So we have a score, the mean is 500. So I'm going to plot 450 here, and I'm going to plot 350 here. Okay, so the percent of cases for the z-score of minus 1.5, go to my table, 1.50 is 43.32. So no problem. I'm going to plot that as 43.32%. My percent of cases for my z-score of 0.5 was 19.15. So I'm going to plot that as 19.15%. Now I want to know the difference between the two, right? Because this is the only percent of the cases I'm interested in. Your z-scores give you the distance between the z and the mean, right? So the area under the curve that it gives you that. So remember what I said on the first one. If your bell curve, you cross the midline, you add. If you didn't cross the midline and you want to know between the two, you subtract the highest minus the lowest. So for this, we're going to do 43.32 minus 19.15. Again, the general rule is if we want to know between 2 points and it stays on one side of the bell curve, never crosses the midline, we subtract highest minus the lowest. So we're going to subtract that. We get 7, 1, 4, a total of 24.17% of the cases occur between 350 and 450. That's it, right? So now we answered question 2. So I showed you when you would add. I showed you when you would subtract when you're comparing between 2 points. Now, if we use the language of above or below, I would say it's important to shade your distribution to see if you're going to add or subtract. I'll show you what I mean. Okay. If I were to ask what percent of the cases get a SAT score above 433? So above 433. So now I want to mark 433 here, draw my line, but what am I looking for? I'm looking for all the scores above. So really, if you don't mind, I'm going to shade the distribution for what I'm looking for. Now, if you see the shading crosses the midline, doesn't it, right? Because here's the midline with 500, right? Now, I have to plot it, drew my bell curve, now I have to calculate. So z-score is 433 minus 500 divided by 100. So we get 67 over 100, right? Which gives me 0.67 in the negative, right? So I need to calculate a z-score that is 0.67 in the negative. Now for this one, I want to take you through it. I said if we go across the top, we get our hundredths place. If we go down, we get our whole number and our tens place. So what I'm going to do is I'm going to hold this up and I need to go to 0.6. So I found 0.6 and then I need to go across to 0.07 right here. So if you see 0.6 down and 0.07 across, you'll see that it's a total of 24.86%. So I'm going to plot that now. In this, we have 24.87%. I'm just going to double check my number. .86%, 24.86. I'm glad I checked. All right. So what that does is gives me the area under the curve between here and here. Now, I have a whole nother side of this bell curve, don't I? 1/2 of the bell curve is 50%. The other half of the bell curve is 50%. Together, it's 100%. So if I'm taking this whole side, I'm going to do 50%. So if I want to know what the percent of cases that get a score of 433 or above it, what I would do is I do 50 plus 24.86. Now the same rule is at play, right? The shading crossed the midline. So now I'm going to add. So I get 74.86%. That's it. So that's how you calculate that. So I hope that that has illustrated what I'm trying to accomplish, right? So the first thing we were doing on this slide was to calculate the distance between when they're on 480 to 220, they're two sides of the distribution we add. The proportion of the population that's between 350 and 450, it's the same side of the distribution, so we subtract, right? And then the last one was proportion of scores that are more than 433. So we calculate the z-score for 433, and then we shade everything that's above it because we want more. And that goes all the way to the other side of the distribution. And because it crosses the midline, we're going to add once again. So the final challenge is to calculate raw scores given a calculate a raw score relative to an area given. So if I were to ask you, what score does a person need to get in order to be in the highest 15% on SAT scores, right? So the highest 15% would be the 85th percentile, right? So we would have to find 35% on the curve. Now this, you don't have a formula for just yet. So the first thing you're gonna do is you're gonna say, okay, what's the closest I get to 35% without passing it? And I discover I get 1.03, a z-score of 1.03. No problem. So what I'm gonna do is I'm going to figure out what the raw score would be for a z-score of 1.03. So the first thing is we're getting the top 15%. So we're going to draw a bell curve. Well, we know this is 50%. The top 15% is going to be somewhere here. We want 35%, right? 50 plus 35 is 85%. And this is your remaining 15%. So your top. Okay. So what is the score you need to get there? So we went in the back of the book, and just to double check, we needed a z-score of 1.03. So we're going to do a raw score formula. X is equal to z times the standard deviation plus the mean, right? I'll do X bar because that's what I did. So let's calculate that. Our z is 1.03 times 100 plus the mean is 500. So we would need 103 plus 500, an SAT score section, that is, of a 603 or above. That would put us at the top 15th percentile. So the z equal to positive 1.03. Does that make sense? So now I've calculated the top 15%, and this is what I'm interested in. So the score would be, here's 500, here's 603. So the score would range between 603 and 800, right? That would be anything that's 603 or above would bring me to the top 15%. Okay, so that's pretty easy. Now we have one more before I let you go. So the last one, right, is when we talk about area in the middle of the distribution. So for this, you want to think of, you know, the highest and the lowest cutoff point, and then what's in the middle, right? So if I were to ask you, what are the cutoff scores for the highest 5% and the lowest 5% of the distribution? Same rules apply. We're going to plot that, right? So I'm going to show you how to do that in a minute. So let me let me get rid of this slideshow. And I want top 5 and bottom 5, right? No problem. Top 5% and bottom 5%. Okay. So what I'm going to do is I'm going to do my bell curve. Now, just as a reminder, you have 50% on each side, right? I want the bottom 5%, and I want the top 5%, the cutoff scores. So what percent is on this side that's left over? If 5 is here, what's 5 off of 50? 45, right? 45% on this side. 5 off of 50 is 45 on this side. And now I need to calculate area under the curve for 45% on both sides. So the same rules apply. So the first, we plot it. Now we need to figure out 45%. And I'm going to go to my area under the curve, and I'm going to find the number that is closest to 45 without overshooting it. So I'm going to go here, 42, 42, 43, 44, 45, up past it. So we're going to go to 44.95, right? That's right before 45. 45.05 is already overshot it. So 1.64. So now I need to calculate the cutoff scores for plus and minus 1.64. So a Z of minus 1.64 and a Z of plus 1.64. And I have to calculate 2 raw scores, right? So my raw score for the first one is going to be minus 164 times 100, which was the standard deviation, plus 500. So that's going to be 164 negative plus 500, which is going to give me 336. So this cutoff score is 336. And then the other cutoff score is going to be in the positive 1.64 times 100 plus 500. So we get 164 plus 500, which will give me 664. So on this end, it's 664. So the question was, what would the raw score have to be the bottom 5%? 336. What percent of the cases, what score would you need to be the top 5%, which is 664? And that, my friends, is our lesson. So I encourage you to practice, because the way we calculate percentile rank, the way we calculate area under the curve, it takes time. So if I'm giving you the raw score, then you have to calculate the Z-score, which is what we did in the first few examples. If I'm asking you the actual score, so now that's a raw score formula, right? So we have to find the percent in the back of the book and then plug in the raw score formula, which I did behind me. So that is our lecture. I hope it makes sense, but if you have any questions, put it in the chat. All right. Take care, everybody.